Almost none of the ice in the Greenland Sea was made in the Greenland Sea. That single fact governs everything else about this water. The flows that grind along the east coast of Greenland were not born there. They were born somewhere north of Siberia, or off the Canadian archipelago, or in the middle of the Arctic Ocean where nobody was watching. And they spent years drifting across the top of the world before they ever came near Greenland. By the time they arrive, they're old. They're hard. They've been squeezed, rafted, ridged, and refrozen so many times that they no longer behave like the smooth white sheet people picture when they hear the words sea ice. And they keep coming. Not seasonally, not occasionally, continuously, through a gap in the map that never closes, on a current that never stops running south. So watch what that does, and note that this one is checkable against any harbor schedule. Take Longyear Buy-in, on the west side of Svalbard, at about 78 degrees north. That is far above the Arctic Circle. It is farther north than the northern tip of Alaska, farther north than almost anywhere people live year-round. And its harbor works. Ships come in through most of the year. Cruise vessels tie up in summer. Coal went out of that coast for a century. Warm Atlantic water runs up the western flank of Svalbard and keeps the door open. Now cross the same sea straight west, about 400 miles, and hold your latitude. You arrive at the northeast coast of Greenland. There's a Danish weather station down there at Danmarkshavn, a little south of that line, and for most of the year the sea in front of it is shut. Difficult would be the generous word. Shut is the accurate one. Supply comes once a year if the ice allows it, and there are years when the ice does not allow it. Same latitude, same planet, same sea, technically. One side has a working port, the other side has a wall. Nothing about the sun explains that. Nothing about the shape of the land explains it either. What explains it is that the Greenland side sits directly under the exhaust pipe of the Arctic Ocean, and the Svalbard side sits under the intake. I want to be honest about the phrase in the title because it's the kind of phrase that gets thrown around and almost never gets settled. Most hostile ice border on Earth. Hostile to what? Measured how? Against which competitors? A superlative that never names its comparison is just decoration, and there are at least half a dozen ice margins on this planet with a legitimate claim to being brutal. So that question gets answered out loud with numbers before this is over. Some of the answers won't go the way the title implies. There are measures where another ice margin beats this one outright, and those get conceded when we reach them. But start with the geography, because the geography is what builds everything else. The Greenland Sea is not the Arctic Ocean, and it is not the North Atlantic. It sits between them, in the gap. Greenland forms its western wall. Svalbard sits on the eastern side. To the north, the sea opens into the Arctic through Fram Strait. To the south, it fades into the Norwegian Sea, somewhere around the latitude of the island of Jan Mayen. Draw that box, and you've enclosed roughly 465,000 square miles of water, which is larger than Texas and California put together. In the middle of it, the seafloor drops to nearly 16,000 feet, close to 3 miles straight down, in a basin most people have never heard of. That's a serious ocean. It has abyssal depth, its own circulation, its own weather, and it spends its entire existence receiving something from upstream. The thing about a current is that it carries what it's given. The East Greenland Current is the western limb of the flow through Fram Strait, and it runs south along the Greenland coast with the cold, low salinity water of the Arctic surface layer riding on top and, sitting on that, the ice. Not a little ice. Measurements from moorings that have been anchored in the strait since 1990 put the average annual ice volume leaving the Arctic through that gap in the neighborhood of 2,000 cubic kilometers, which works out to something close to 500 cubic miles a year. That number does nothing until you put it against something you can picture, Lake Erie holds about 116 cubic miles of water. So the Arctic pushes roughly 4 Lake Erie's worth of ice, as ice down this coast every single year, and it arrives in solid pieces, moving. You cannot build a harbor under that. You cannot schedule around it reliably. You can only work in the gaps it leaves you, and the gaps are not on a calendar. There's a particular kind of misunderstanding that comes from looking at maps of Arctic sea ice on the news. Those maps show extent, a white blob that grows in winter and shrinks in summer, and they give the impression of ice as a lid that sits still and breathes. Ice does not sit still. The Arctic pack is in constant motion, spun by wind and by the currents underneath, and one enormous conveyor runs right across the pole from the Siberian side toward the Atlantic. Oceanographers call it the transpolar drift. Everything that drift carries eventually reaches the same exit, because there's essentially only one deep exit available. Fram Strait is that exit, about 280 miles wide between northeast Greenland and the northwest corner of Svalbard, with a sill deep enough, roughly 8,000 feet, to let water move between the Arctic and the Atlantic at depth, instead of merely skimming across the top. Every other connection the Arctic has to the world ocean is either shallow, narrow, or both. The Bering Strait is about 160 feet deep and 50 miles wide, which is a keyhole. The channels of the Canadian archipelago are a maze of shallow sills. Fram Strait is the real door, and it opens onto the Greenland Sea. So the sea we're talking about isn't a place where ice happens. It's a place where ice is delivered. And that difference, which sounds like semantics for about 10 seconds, turns out to explain the ships that were crushed here, the settlements that go 9 months without a boat, the weather that killed 79 men in a single April night, and, at the far end of all of it, a patch of ocean, where the surface water goes down to the seafloor and begins a journey that touches the climate of half the world. We're going to follow the ice. Not jump around the map, not tour highlights. Follow it, the way you'd follow a river, from the moment it squeezes through the strait to the moment it finally stops existing somewhere off the southwest tip of Greenland, thousands of miles later, having changed the ocean it melted into. The rules change as we go south. That's the part people miss. The Greenland Sea is not one hazard repeated over and over. It's a sequence of different hazards, handed off from one latitude to the next. And the thing that will kill you at 79 degrees north is not the thing that will kill you at 65. At the top, it's the ice itself, thick, old, and dense enough to crush a hull that was built to resist it. In the middle, it's the wind. And the wind here does something almost nowhere else on Earth does, because it comes off the highest ice sheet in the northern hemisphere and falls. Farther south, it's the water temperature combined with spray, which sounds mild and is not, and which has capsized vessels that were in no other trouble at all. And at the bottom of the run, the danger changes category entirely. It stops involving the ice at all, and starts involving what the melted ice does to the ocean underneath. Start at the door. Fram Strait is one of those places where two completely different oceans are forced to share a hallway. On the eastern side, hugging Svalbard, the West Spitsbergen Current carries Atlantic water north. This is warm water by Arctic standards, often somewhere between the upper 30s and the mid-40s Fahrenheit. Salty, dense, and it's the last northbound leg of the same system that carries heat up from the tropics. It goes into the Arctic Ocean, slides underneath the fresher polar surface layer, and disappears from view as a warm, intermediate layer that circles the entire Arctic basin. On the western side, against Greenland, everything runs the other way. The East Greenland Current comes south out of the Arctic, carrying cold water, low salinity water, and the ice. Volume transport near the top of that current has been measured at around 8.5 sverdrups, and a sverdrup is 1,000,000 cubic meters per second, which means the number in front of you is roughly 8.5 million cubic meters of water crossing an imaginary line every second. For comparison, the Mississippi River at its mouth averages under 20,000 cubic meters per second. So the southbound flow along the Greenland side of this strait moves several hundred times the water of the Mississippi. Between those two, in the middle of the strait, the flows tangle. Some of the Atlantic water turns around and joins the southbound side. Some of the polar water gets pulled east. Anyone hoping for a clean pipe with an in lane and an out lane will be disappointed. Where the warm and cold water meet, you get eddies that spin off and wander for months. The middle zone matters for one reason. Warm Atlantic water arriving under a flow from below will melt it, and the amount of Atlantic influence reaching the East Greenland side has been changing. You don't get a claim like that out of a model. You get it by putting instruments in the water and leaving them there for decades. Which brings up a question worth sitting with for a second. How does anyone actually know how much ice comes through here? You cannot count flows from a boat. Satellites see the top of the ice and the area it covers, and they see it drift. But from orbit, you cannot see how thick something is when it's floating with 90% of itself underwater. Thickness is the whole game. Area times thickness is volume, and volume is what actually matters for how much fresh water gets delivered to the North Atlantic. So the solution was to put listening devices on the seafloor and point them up. Since 1990, moorings have been anchored across the western part of Fram Strait, near 79 degrees north, carrying instruments called upward-looking sonars. The device sits well below the surface, sends a pulse straight up, and times the echo off the underside of whatever is floating above it. If it hits open water, the echo comes back at one travel time. If it hits the bottom of a flow, it comes back sooner. Do that every few seconds for a year, while the ice drifts overhead at a known speed, and what you get is a profile of the underside of the Arctic ice pack as it exits into the Atlantic. Every ridge, every lead of open water, every keel. That record now runs more than 30 years. And it's one of the longest continuous physical measurements of the Arctic that exists. It's also, in a very unglamorous way, brutal to maintain. Somebody has to sail a ship into Western Fram Strait, find the mooring, trigger an acoustic release, wait for a package of instruments to float up through possibly ice-covered water, and recover it before it drifts under a flow. Then put a fresh one down, once a year, in one of the least forgiving pieces of water in the hemisphere. 30-odd years of a data set means 30-odd years of somebody making that trip and getting it right. What the sonars found is worth stating carefully, because there are two different things going on, and they get blurred together constantly. The first is thinning. Comparing the same instruments in the same place, the typical thickness of the older perennial ice-crossing Fram Strait in winter dropped from around 11 feet on average in the 1990s to something closer to 7 feet in the winters between 2005 and 2011. The modal thickness, meaning the value that shows up most often in the distribution rather than the average, fell by something like 15 to 20% per decade across the 1990 to 2014 record. In late summer more recently, the ice coming through has run thinner still. The second thing is that the total volume going out has not simply collapsed in step with that, because thinner ice moves faster and more of it gets pushed through. Thinner ice, more of it. Roughly similar volume in some years, which means the delivery to the Greenland Sea has continued while the individual pieces got weaker. If you're on a ship, those two facts pull in opposite directions and neither one saves you. Thinner ice is easier to break. Faster moving ice is harder to escape. A ship beset in a slowpack has time. A ship beset in ice that's moving 25 miles a day toward a coast has considerably less of it. Drift speeds through this strait, measured by satellite tracking of ice features and by the buoys people plant on flows, generally run somewhere between about 1/3 of a foot and 1.5 feet per second. Put that in daily terms, and you get roughly 5 to 25 miles a day of southward motion. In a hard northerly blow, it goes higher. I want you to hold that in your head against the mental image of pack ice as a static white plane, because the difference is the difference between a parking lot and a conveyor belt. If a vessel gets caught in Fram Strait in winter, it does not stay in Fram Strait. It goes south at the speed of the ice, and it has no say in the matter. There is a name for the pieces that come through here, at least among people who work in ice, and the distinction is not academic. First-year ice is ice that formed since the previous autumn. It's still salty because when seawater freezes, the salt doesn't fit neatly into the crystal structure and gets trapped in pockets of concentrated brine within the ice. Those brine pockets make first-year ice comparatively soft. It fractures. A capable hull can push it aside. Multi-year ice has survived at least one melt season. Over the summer, meltwater on the surface drains down through the ice and flushes those brine channels out. What's left is dense, nearly fresh, and much harder. It behaves less like frozen seawater and more like structural material. Old multi-year flows are what people mean when they talk about ice that can hold a ship, and the transpolar drift delivers them to Fram Strait by the thousands. Then there are the ridges, which are the actual problem. When two flows are pushed together, the ice at the boundary fails and piles. Some of it goes up into a rubble wall, a sail, and some of it goes down into a keel. And because ice floats with most of its bulk submerged, the keel is always the bigger structure. Sail heights of a few feet imply keels many times deeper. In heavy Arctic ridging, keel depths of 60 feet and more below the waterline have been recorded, and in extreme cases considerably deeper than that. A ship sitting in flat ice is in a manageable situation. A ship sitting in a field of ridges, when the whole field starts to converge because the wind shifted, is in a completely different one. And the record of what happens then is not theoretical. There are ships on the bottom of this sea, and there are logbooks describing what the hull sounded like on the way down. Those logbooks are coming. Before we follow the ice down to the coast where they were written, though, the word hostile needs to be forced to justify itself because right now it's doing an enormous amount of work without showing any of it. Hostile is a comparative word, and a comparative word without a comparison is an empty one. So let's set up the yardstick properly and then run this margin against the real competition, including the cases where it loses. Hostile to what? Not to life. That would be the wrong question, and it would produce the wrong answer, because the Greenland Sea ice margin is biologically rich. Ice algae grow on the underside of the floes. The melting edge triggers plankton blooms. Polar cod live in the cracks, and seals pup on the drift ice by the hundreds of thousands. Ringed seals, harp seals, hooded seals, and the bears that follow them. The ice edge is a feeding ground, and a productive one. Life is not fighting this place. Life is exploiting it. So the honest framing is hostility to human operation, to ships, aircraft, structures, crews, instruments, and the ability to get any of those out again once something goes wrong. That's a definition you can actually measure, and it breaks down into 5 things. 1. The character of the ice itself, meaning thickness, age, hardness, and how much of it is multi-year. 2. How fast the ice moves and whether it converges, which decides whether besetment means waiting or means being crushed. 3. Whether the coastline offers refuge. A lee shore with harbors is a bad day. A lee shore with no harbors is a different category of problem. 4. The weather regime. Specifically, whether the local atmosphere produces sudden extreme events that are hard to forecast. 5. How far away help is, and whether help can physically reach you. Now the competitors, and there are real ones. The Labrador and Newfoundland ice front is seriously dangerous water, and it has the casualty history to prove it. Sealing disasters there in the early 20th century killed men by the dozens. But the ice at that front is overwhelmingly first-year ice grown locally in the Labrador Sea and the Gulf of St. Lawrence. It's thinner, softer, and it disappears every summer. There are also ports, St. Anthony, St. John's, a whole coast with harbors, and a coast guard that flies helicopters. That last part changes the arithmetic completely. Baffin Bay and Melville Bay, up the west side of Greenland, beat the Greenland Sea on one specific measure, and it's worth conceding cleanly: iceberg density. The glaciers of West Greenland are the most productive iceberg factories in the Northern Hemisphere, and the northeast corner of Baffin Bay in summer is a genuine minefield of them. If your definition of hostile is the density of hull-killing bergy bits per square mile, Melville Bay wins in the north, and the historical whaling fleet losses up there are the evidence. The Sea of Okhotsk and the Bering Sea produce more vessel icing casualties than the Greenland Sea does, and by a wide margin. That's partly physics and partly exposure. There are hundreds of fishing vessels working those waters in winter, and only a handful working the Greenland margin. But the underlying spray icing conditions in the Okhotsk are ferocious, and pretending otherwise would be dishonest. On that measure, on freezing spray specifically, the Greenland Sea does not hold the record. And then there's the Weddell Sea, which is the serious challenger. The Western Weddell on the Antarctic side has the thick multi-year ice. It has a gyre that traps you and carries you in a circle rather than releasing you. And it has an isolation that the Northern Hemisphere simply cannot match. When the Endurance was crushed there in 1915 and Shackleton's men went onto the ice, there was no possibility of anyone coming for them because nobody knew where they were, and nobody had the means. 3 years earlier, the German ship Deutschland had been beset in the same sea for 8 months before the pack let it go. 8 months. In the Greenland Sea, a beset ship is usually delivered somewhere within weeks because the current keeps moving it south toward warmer water. So take the concession plainly on isolation, on the duration of besetment, and on the impossibility of rescue. The Weddell Sea beats the Greenland Sea, and it isn't close. Anyone who tells you otherwise is selling something. What the Greenland Sea has, and what nothing else on the list has all at once, is the combination. It receives the oldest and thickest ice that exists in the Northern Hemisphere, because it's downstream of the entire Arctic Ocean, and every other exit is too shallow to pass it. That ice arrives moving, at speeds that can reach 25 miles a day, driven by a current that never reverses. It arrives against a coastline more than 1,000 miles long that has, in practical terms, no harbors, no refuge, no deep-water port, and almost no people. And the ice is being pushed onto that coast rather than away from it. And that coastline is the edge of an ice sheet 2 miles thick, which generates a category of wind event that the Labrador Front, the Bering Sea, and the Weddell Coast do not produce in the same way. That last part deserves its own passage later, and it gets one, because it's the most underappreciated thing about this margin. Add it up and you get an operating environment where the ice is at its hardest, its motion is at its most relentless, the shore behind you offers nothing, and the atmosphere above you can go from calm to survival conditions inside an hour. As a place to be a human being with a job to do, the East Greenland ice margin is the most hostile ice border in the Northern Hemisphere, and I'd defend that claim against every northern competitor on the list. Extend it to the whole planet and it becomes arguable rather than settled, because the Weddell exists. And honesty requires leaving that argument open. There's one more thing the yardstick has to account for, and it's the reason this margin keeps generating stories, while other severe ice zones quietly don't. People keep going there anyway. Nobody has a commercial reason to be in the Western Weddell Sea. Almost nobody lives within 1,000 miles of it. The East Greenland margin, by contrast, has had continuous human presence and human traffic for a very long time. Inuit communities on the coast, Norwegian and Danish sealers working the drift ice between Jan Mayen and Greenland for well over a century, trappers wintering in huts along the northeast coast, weather stations, scientific moorings that have to be serviced annually, fishing vessels working the edge, military patrols. A place is only dangerous in a way that matters if people are in it. And people are in this one constantly, which makes the record of what happened to them the best evidence available about what the place actually does. So we go south with the ice, and we start where the ice first touches Greenland, on a stretch of continental shelf that behaves unlike almost any other coastal water in the Arctic. It's wide, it's shallow in patches, it's carved by ancient glacial troughs, and for most of the 20th century it was locked under a sheet of fast ice, so stable that it functioned as a piece of the continent. That sheet has a name, and it has spent the last 30 years falling apart. South of Fram Strait, the ice meets Greenland for the first time, and Greenland here does something unexpected. It gets wide. The continental shelf off northeast Greenland extends out from the coast for up to 190 miles. That's a lot of shallow water in a region people tend to imagine as a cliff dropping straight into the abyss. And this shelf isn't flat. It's been carved by ice sheets that came and went over hundreds of thousands of years, and what they left behind is a set of deep, arcing troughs cut into the shallow bank, running inland like sunken canyons. Two of them matter for what happens here. The west wind trough runs in from the north. The Norske trough comes in from the south. Between and around them sit the shallow parts. Belgica Bank, the North Wind Shoal, and Arise, the German research institute that mapped it named after itself. The two troughs converge inland at an embayment in front of a floating glacier tongue, and that geometry turns out to control something important, which we'll come back to. For now, the shallow part is what governs the ice. When a flow drifting south hits water shallow enough that its keel touches bottom, it stops. It grounds. And once a few big flows ground on a bank, the ice between them stops moving too, and the whole assembly begins to freeze together into a single sheet. Ice that's attached to the coast or grounded in place and no longer drifting is called fast ice, from the old sense of the word meaning held fast, fixed, immovable. It's the same root as steadfast, and it's a good description, because fast ice is the one kind of sea ice that behaves like land. Over Belgica Bank, at around 79.5 degrees north, that process built something remarkable. A sheet of landfast ice hundreds of miles across, anchored on the shallows, refreezing every winter and surviving through the summer, year after year, decade after decade. It's known as the Norske or Ice Barrier, named for a group of islands along that coast. For most of the 20th century, the barrier simply did not break. It was there in the summer the way a peninsula is there in the summer. Records indicate it disintegrated once during the 1950s and then held for 4 more decades. In 1997, it broke up. And then it kept breaking up. 2001 through 2005, 2008, 2010, through 2014. What had been a once-in-a-generation event became something closer to the normal state of an East Greenland summer. The explanation researchers give is a combination of warmer air, slowing winter growth, and speeding summer melt, with wind then doing the demolition on a weakened sheet. That's a causal chain with observational support behind each link, and it's about as clean as attribution gets in this field. The bookkeeping is the least of it. Behind that barrier sit 2 of the largest floating glacier tongues in the northern hemisphere. One is the Nordhalvfjordsfjorden Glacier, which is a genuine mouthful, and which almost everyone, including the scientists who study it, calls 79 North Glacier. The other is Zachariae Istrom, immediately to the south. Both are the seaward ends of the northeast Greenland ice stream, a river of ice that drains an enormous share of the interior ice sheet and reaches hundreds of miles inland. A floating glacier tongue is a fragile thing. It's ice that's left the bedrock and is now afloat, held together partly by its own strength and partly by whatever is pressing against it. Thick, Immobile sea ice packed against the front of a floating tongue provides back pressure. It gets in the way of calving. When the sea ice in front of a tongue is a solid barrier that doesn't move for years, the tongue is buttressed, and the glacier behind it discharges more slowly. When that barrier breaks up every summer, the buttressing goes away. Zachariah Istrom's floating section has largely collapsed since the mid-1990s. 79 North has been thinning and losing area from underneath, with warm Atlantic water reaching it through those glacial troughs I mentioned. That's the geometry paying off. The Norski Trough works as a delivery channel, letting comparatively warm water from the Atlantic layer travel across the shelf, under the fast ice, and reach the underside of the glacier tongue where nobody can see it happening. So on this stretch of coast, there are two entirely different ice systems interacting, and they feed the same current. Sea ice arriving from the Arctic and glacier ice arriving from the interior of Greenland, and both of them end up going south in the East Greenland Current together. That mixture is part of what makes this margin harder than a pure sea ice margin. Sea ice, even hard multi-year sea ice, is still frozen ocean, and a hull designed for it can generally survive contact with it. Glacier ice is different material. It's compressed snow, thousands of years old, fresh water, with the air squeezed out of it, and it's dense and hard in a way that sea ice never manages. A piece of glacier ice the size of a car, floating with almost all of itself underwater, has been enough to end vessels that were operating perfectly well in surrounding pack ice. The technical vocabulary for the small stuff earns its place here. An iceberg is the big one. A burgee bit is roughly house-sized, and a growler is the small one that rides low, shows almost nothing above the surface, and is nearly invisible on radar in a seaway. The name is not a joke about attitude. It comes from the sound they make, a low growl. When air trapped in the ice escapes as it melts, growlers in a swell at night, in a region where the ice charts are updated by satellite pass rather than continuously, are the hazard on this coast that gets the least attention relative to how often it nearly matters. The northeast coast also carries almost no people, and that emptiness is worth a moment, because history put it there, and geography only helped. There were Inuit communities along the northeast Greenland coast in the past. Archaeology and the accounts of early expeditions record the remains of settlements, dwellings, and hunting sites far up that coast, in places nobody lives now. The population declined and eventually vanished from that stretch, and when Denmark later established its claim over the region, the area was administered as a national park with no permanent civilian population. In 1925, a group of families from the Ammassalik region farther south, along with some from the west coast, were resettled to found a town at the mouth of a huge fjord system in central East Greenland, partly to strengthen the Danish claim to the coast. That town still exists. We'll get there, because how those people live tells you more about this sea than almost anything else does, and it doesn't fit the story most people expect. But at 79 degrees north, there's essentially nobody. A weather station. A military patrol that runs dog sledges across an enormous district. Research camps that come and go with the season. And beyond that, a coastline of fjords and nunataks and glacier fronts running south for hundreds of miles, with nothing on it but the ice going past. Which raises a question that took the better part of a century to answer. And the answer arrived in the strangest possible way. Where does all this ice actually come from? And how far does it travel? In 1879, an American naval steamer called the Jeannette pushed north through the Bering Strait, aiming for the pole. The prevailing theory of the day held that there was an open polar sea up there, warm water beyond a barrier of ice, and that a ship which got through the barrier would find sailing room. That theory was wrong, and the Jeannette proved it the hard way. She got caught in the pack north of Siberia in September of 1879 and never got out. For 21 months, the ice held her and carried her in loops and reversals, generally northwest. In June of 1881, near the New Siberian Islands, the pressure finally beat the hull and she went down. The crew took to the boats and sledges, and what followed in the Lena Delta was one of the grimmer episodes of 19th century exploration. The commander, George DeLong, and most of his party died there. 3 years later, in June of 1884, a hunter near Julianahab, on the southwest coast of Greenland, found debris on a drifting floe. Not driftwood, not general wreckage, clothing with crew names on it. A list of the Jeannette's boats in DeLong's own handwriting, documents signed by him. The items were examined and judged unquestionably genuine. Take a second with the geography of that, because it's the whole point. The Jeannette sank off the New Siberian Islands, which is on the opposite side of the Arctic Ocean. The relics turned up near the southwestern corner of Greenland. The distance between those 2 points, going the only way ice can go, is something like 2,900 nautical miles, and the material made that trip in about 3 years, frozen into a floe, without anyone steering it. That find rearranged Arctic science, and it did it by accident, because it meant something specific. There's a current running clean across the Arctic Ocean, from the Siberian side to the Atlantic side, and it exits by Greenland. The Norwegian meteorologist Henrik Mohn worked the implications out and published the idea of a transpolar drift the same year, and a young Norwegian named Fridtjof Nansen read it and had a thought that most of his professional contemporaries considered close to suicidal. If the ice carries things across the pole, build a ship that can survive being carried. Nansen's plan was to deliberately sail into the pack on the Siberian side, deliberately get frozen in, and deliberately allow the drift to take the ship wherever it went, for however many years that took. When he presented it publicly around 1890, the reception from established polar men was withering. Adolphus Greely, an American with his own hard experience of the Arctic, called the scheme illogical. The general view was that the ice would crush the ship exactly as it had crushed the Jeannette, and that Nansen would be adding his own name to a long list. The answer to that objection was in the hull. Nansen worked with the shipbuilder Colin Archer to design a vessel with a rounded, almost bowl-like cross-section and no sharp turn of the bilge, extremely heavily framed, with the idea that when the ice squeezed, the pressure would find no flat surface to grip and would instead push the whole ship upward, out of the vice, rather than in. The ship was named Fram, which means forward in Norwegian. She sailed in 1893, entered the ice off the New Siberian Islands in September, and drifted for 3 years. The hull worked. When the pack closed on her, she rose. Nansen and Hjalmar Johansen eventually left the ship to make a dash north on foot and by dog sledge, got farther north than anyone had been, ran out of viable route, and spent a winter in a stone and walrus hide hut in Franz Josef Land, eating bear and walrus, before an English expedition stumbled across them in the summer of 1896. The Fram herself emerged from the pack north of Spitsbergen in August of that year, having drifted to nearly 86 degrees north. Both parties reached Norway within about a week of each other, entirely by coincidence, having been out of contact with each other for a year and a half. That story is famous. What gets less attention is the piece of physical oceanography it delivered. The Fram's 3-year drift, with continuous observations, established the transpolar drift as a measured reality, no longer an inference resting on one lucky find. And Nansen's data on how the ice moved relative to the wind led directly to some of the foundational work on how the ocean responds to wind stress at high latitudes. A trip that was sold as an attempt on the pole failed at the pole and succeeded enormously at everything else. There's a modern echo of the Jeannette relics that I've always enjoyed, and it involves bath toys. In January of 1992, a container ship crossing the North Pacific hit heavy weather and lost containers overboard. One of them held roughly 29,000 plastic bath toys, ducks and turtles, and frogs and beavers, and the container broke open. Two oceanographers, Curtis Ebbesmeyer and James Ingram, realized they'd just been handed an enormous free drift experiment, and they started tracking where the toys came ashore using beachcomber reports. The toys turned up in Alaska. They turned up along the coast of British Columbia. And Ebbesmeyer predicted, based on the same circulation that Jeannette relics had revealed a century earlier, that some fraction of them would go north through the Bering Strait, get frozen into Arctic sea ice, ride the transpolar drift for years, and eventually be released into the North Atlantic through the Greenland Sea. Reports of finds on North Atlantic shores did surface years later, and I'll be straight about the evidence. Individual beach finds of an unmarked plastic toy are close to impossible to verify, and the Atlantic arrivals were never confirmed the way the Jeannette relics were confirmed with names and signatures. What the episode does illustrate perfectly, and what it was actually useful for in current modeling, is the route. Anything that gets into the Arctic pack from anywhere is on a conveyor with one main off-ramp, and that off-ramp opens onto the sea we're looking at, which is a slightly whimsical way of arriving at a serious operational point. The ice that arrives on the East Greenland coast is not local ice with local properties. It's a sample of the entire Arctic Ocean, gathered over years, concentrated by a current, and delivered to one coastline. That's why a mariner in the Greenland Sea encounters ice that has no business being that hard at that latitude, in a place where the calendar says spring. The people who found that out first didn't have satellites, ice charts, or a radio. They had a wooden ship and a chronometer, and several of them wrote down exactly what happened in a way that still reads as a warning. In June of 1869, two German ships left Bremerhaven together, headed for the east coast of Greenland. The expedition was led by Carl Koldewey, and it had a straightforward goal for its era: get up the coast, map what nobody had mapped, and see how far north a ship could push. The Germania was a steamer. The Hansa was a sailing vessel under Captain Paul Hageman. The plan was for them to stay in company. On the 20th of July, in thick fog off the ice edge, the Germania made a signal. The Hansa read it, understood it to mean one thing, and acted on it. It had meant something else. When the fog lifted, the two ships were no longer in sight of each other, and they never found each other again. The Germania went on to have a hard but successful season. She wintered near Sabine Island, off the northeast coast, and her crews sledged north the following spring and put a stretch of coastline on the map that nobody had described before, including a large fjord system they named for the Austrian emperor. She came home in September of 1870 with her science done. The Hansa's season went differently. She worked into the ice, looking for the Germania, and the ice took hold of her. By mid-September of 1869, she was fixed in a floe and going wherever the floe went, which was south. The pressure started working on the hull. Not all at once. Over days, then weeks, with the sound of it audible through the timbers, and Hageman had enough warning to do the one intelligent thing available. He began moving everything onto the ice before the ship was gone. Provisions came out, boats came out, and then the crew did something that I have never encountered anywhere else in the polar record. Part of the Hansa's cargo was patent fuel, coal dust pressed into hard rectangular blocks for a steamer's bunkers. Faced with the need to build a shelter on a floe with no timber to spare, they built a house out of the coal bricks, a coal house on drifting sea ice. In the Greenland Sea, in October. The Hansa went under in the second half of October, 1869. 14 men were left standing on a piece of ice off the coast of Greenland with the winter in front of them. What happened next lasted about 200 days. The floe drifted south with the East Greenland current, at the speed the current dictated, which is exactly the speed we've been talking about, and it carried them the length of the coast, down past the latitudes where the Germania was wintering, down past the mouths of the great fjords, down through the drift ice belt as it widened. The floe itself was consumed by the journey, cracking and shrinking, and more than once they had to move camp onto a sounder piece. The coal house did not survive the whole trip. They spent Christmas on the ice. They celebrated it, according to the account, with a small tree improvised from whatever was to hand. In May of 1870, with the floe no longer a viable platform, they took to the boats. And on the coast southwest of Cape Farewell, in June, they reached a Moravian mission station and walked into a building for the first time in nearly 8 months. All 14 survived. That's the part that stops me every time. They had crossed more than 1,000 miles, sitting on a raft they did not choose and could not steer through an Arctic winter. And the entire ship's company came out the other end alive. It's the best argument I know that competence and unglamorous preparation beat heroics, because nothing about that drift was heroic in the movie sense. It was rationing, discipline, shelter, and not panicking, repeated daily for 200 days. It also demonstrates the East Greenland current more convincingly than any instrument could. 14 men and a coal house went in at the top and came out at the bottom on schedule. 40 years later, the same coast produced a story that went the other way on almost every count. In 1909, a Danish explorer named Einar Mikkelsen sailed north in a 45-ton steam sloop called the Alabama with a small crew. His purpose was specific, and it was, in a way, an act of respect for the dead. The Denmark expedition of 1906 to 1908 had worked this coast, and 3 of its men, including its leader Ludvig Melius Eriksson, had died in the far north of Greenland on a sledge journey. Their records were still out there, cached in cairns. Mikkelsen intended to go and get them, because those records settled a real geographic question about whether a channel cut across the top of Greenland, as an earlier map had claimed, or whether the land was continuous. The Alabama got as far as Shannon Island on the northeast coast, and there the ice took her. In August of 1909, the crew moved ashore. Mikkelsen and the ship's engineer Ivar Iverson set out by sledge and were gone for about 7 months. They covered an enormous distance, they found the cairns, they recovered the records, and they came back starving, having eaten most of their dogs, in a condition their own account describes without drama and which reads worse for the restraint. They arrived back at Shannon Island to find the Alabama wrecked and the rest of the crew gone. The others had been picked up by a Norwegian sealing vessel and had gone home, leaving a note. The 2 of them were now alone, on the northeast Greenland coast with a broken ship. So they took the Alabama apart and built a hut out of her. Then they waited, through a winter, then another summer, during which no ship came, because the ice on that coast decides who arrives and when. Then another winter, then a third. A Norwegian sealer found them in the summer of 1912. They'd been out there roughly 3 years, and the records they'd gone to retrieve were intact and came home with them, which corrected the map of northern Greenland. Put those 2 stories side by side and you get the whole character of this margin in one comparison. The Hansa's crew were carried 1,000 miles. They never intended to travel because the ice here moves. Mikkelsen and Iverson sat in one place for 3 years they never intended to spend, because the ice here also blocks. Same sea, same current, opposite failure modes, and both of them are consequences of the same physical fact, which is that the ice is arriving continuously from somewhere upstream and the coast has no way to shed it. There's a detail in the Mikkelsen story I keep coming back to. The reason no ship reached them for 2 summers wasn't a lack of will. Relief attempts were made. The ice simply didn't open in the right place at the right time, and a wooden sealer of that period could not force it. That is not a 19th century problem that technology has since retired. Modern vessels get stopped on that coast too. In 2020, a supply ship serving the East Greenland settlement of Itok Kortormiet sat stuck in ice for 2 days in front of the town it was trying to deliver to, in October, with the whole community watching from shore. The ice got no easier between 1869 and today. What changed is that we can see it coming. Seeing it coming, as it turns out, is a whole discipline of its own. And it started because of something that happened on a Friday night in April of 1952. Between the island of Jan Mayen and the coast of Greenland, in the drift ice belt around 72 to 74 degrees north, there's a stretch of moving pack that Norwegian mariners have called the West Ice for generations. It's called that because there's an East Ice in the Barents Sea, and for a long time both names described workplaces rather than geography. Every year in late winter, harp seals and hooded seals gather on the drift ice of the West Ice to give birth. They need ice that's solid enough to hold a pup and unstable enough to keep predators uncertain, and the East Greenland drift ice delivers exactly that. The concentration of animals on those floes in March and April is one of the larger marine mammal gatherings in the Northern Hemisphere. Where animals gather in numbers, people follow, and Norwegian sealing vessels worked the West Ice for well over a century. It was seasonal, it was dangerous, it paid, and it was woven into the economy of specific coastal communities in northern Norway and along the western fjords. Whole towns sent their men out in March. In the spring of 1952, the Norwegian fleet was in the West Ice as usual. On the 4th of April, a storm came through. It was not forecast in any useful way because in 1952, nothing existed that could have forecast it. There were no weather satellites. The observing network over the Nordic seas consisted of scattered ships, a handful of coastal stations, and the island of Jan Mayen. A weather system that forms in a few hours over open water 200 miles from the nearest observer was, for practical purposes, invisible until it was on top of you. 5 vessels disappeared: the Ringsel, the Bratand, the Varglim, the Buskoy, the Pels. Between them, they had 78 men aboard. The search that followed ran for about 5 weeks and involved aircraft and naval vessels. It found nothing: no hulls, no boats, no wreckage that could be tied to any of the 5. The names of the dead were published on the 7th of May. 79 men in total, counting a loss from another vessel, most of them from the Troms region in the north and from Sunnmøre on the western coast. The number I keep returning to is a different one. 98 children lost their father in that single storm. I'm not going to dramatize what those crews experienced, partly because it would be indecent and partly because nobody knows. There's no wreck, no log, no survivor account. What we can do, and what Norwegian meteorologists eventually did, is understand the thing that killed them, and that understanding is now the reason it happens less often. The storm was a polar low. Polar lows are a category of weather system that the general public has largely never heard of, and they're one of the reasons the seas around the East Greenland ice margin behave the way they do. The mechanism is satisfyingly simple once you see it. The Greenland Sea in winter has an ice edge with very cold air sitting over it. Air that's been over the ice pack, or worse, that's poured off the Greenland ice sheet, can be far below 0 Fahrenheit. Just east of the ice edge is open ocean, and that open ocean is being warmed from below by the Atlantic water coming north. Surface water there might be in the high 30s or low 40s. Now push that frigid air out over that water. The temperature difference between the air and the sea surface can exceed 40 degrees Fahrenheit, sometimes considerably more. Cold air over warm water is unstable in the most basic way a fluid can be unstable. The heavy stuff is on top, and the light stuff is underneath. Heat and moisture pour upward off the sea into the air, enormous quantities of both. Convection starts, and if there's any rotation available in the flow to organize it, the convection wraps itself into a spiral. What you get is a compact, violent, maritime cyclone, typically somewhere between 100 and 400 miles across, which is small, sometimes with a clear eye, and spiral bands that look startlingly like a miniature tropical hurricane in a satellite image. Winds at or above hurricane force, steep, chaotic seas, heavy snow that drops visibility to nothing, and a lifespan of perhaps 12 to 36 hours from formation to collapse. They've been nicknamed Arctic hurricanes, which is a reasonable description of the wind field and a misleading one about the origins, since the energy source is the sea-to-air heat flux over ice-free water in an outbreak of polar air rather than the deep, warm ocean of the tropics. Two properties of these storms make them lethal to small vessels specifically. The first is speed of development. A polar low can go from nothing recognizable to full intensity in 6 to 12 hours. There's no multi-day approach, no falling barometer over 2 days, no time to run for shelter. Before satellites, the first indication a sealing crew had was the weather arriving. The second is where they form. They form off the ice edge, and that location is part of the recipe: bitter air over the pack, open water immediately beside it, and a large temperature contrast between the two, which means the exact region where the seals whelp, where the sealing fleet worked, where the fishing fleet works, where the ice charts matter most, is also the preferred nursery of the storms. After 1952, and after further losses in later years, forecasting polar lows became a serious priority for the Norwegian Meteorological Institute, and the satellite era eventually made the invisible visible. You can now see a polar low spinning up in an infrared image. Forecast models resolve them imperfectly, and warnings go out. Lead times are still short compared to an ordinary Atlantic depression, because you cannot warn far in advance about something that doesn't exist yet, and small-scale systems remain hard for models to place precisely. But the difference between no warning at all and a few hours of warning is, in this business, the difference between a fleet at sea and a fleet in shelter. That's the reframe this whole margin keeps offering, and it's the reason dread is the wrong response to it. The Greenland Sea did not become safer because it became gentler. It became more survivable because people identified specific mechanisms, measured them, and built systems around them. Polar lows still form. Nobody has to be surprised by them anymore. The west ice sealing that those crews died doing has essentially ended now for reasons of economics, regulation, and public opinion. None of them danger. The last Norwegian vessels working that ice sailed within the past decade or so, and the tradition that sent men north every March has closed. What remains out there in April is the ice, the seals, and the storms that form at the edge. There's a second wind system on this coast that no satellite invented and no forecaster fully tames. And it doesn't come from the sea at all. It comes down off the ice sheet. And it's the reason this margin outranks its competitors in the north. Picture Greenland as an ice dome, with a rim of rock showing around the edges. That's closer to the truth than the usual image of a landmass with a white cap on it. And the dome is the thing that matters here. The Greenland ice sheet covers roughly 80% of the island. At its highest, it stands over 10,000 feet above sea level, which puts the middle of Greenland at the altitude of a serious mountain range, except that it's a smooth dome hundreds of miles across rather than a set of peaks. Underneath it, in places, the bedrock has been pushed down below sea level by the sheer weight. Now think about the air sitting on top of that. Snow is close to a perfect radiator in the infrared. On a clear night or through the long polar darkness, the surface of the ice sheet radiates heat to space and gets extremely cold, and it cools the layer of air in contact with it. Cold air is dense air. Dense air on a slope does what any dense fluid does on a slope. It flows downhill. That's a katabatic wind, from the Greek for going down, and it happens on every ice sheet and every glacier on Earth. Over Antarctica, it produces some of the most persistent surface winds on the planet. Over Greenland, it produces something with a local character because of what the edge of Greenland looks like. The rim of the island is a wall of mountains cut by deep fjords, and the fjords act as drains. Air pooling on the interior plateau finds those channels and pours through them, and a fluid squeezed into a narrowing channel speeds up. By the time that air reaches the coast, it has been accelerated by gravity down a slope of thousands of feet and then compressed into a fjord mouth. On the southeast coast, in the Ammassalik district, they call the result a pittorak. The word comes from Greenlandic and carries the sense of something that attacks you. A pittorak is a katabatic wind with synoptic help behind it. When a low-pressure system passes to the southeast of Greenland, the pressure pattern it sets up pulls in the same direction. The cold air already wants to go, and the two effects stack. The drainage flow that would have been strong becomes something else entirely. On the 6th of February, 1970, the town of Tasiilaq took the worst pittorak anyone has documented in Greenland. Take only what can be stood on. The town's anemometer, before it was destroyed by the wind it was measuring, recorded a mean wind speed of about 54 meters per second, which is roughly 121 miles an hour, with gusts around 70 meters per second, about 157 miles an hour. Those are recorded values. The figure most often quoted for that event is 90 meters per second, about 200 miles an hour. That number is an estimate, made after the fact, and it exists precisely because the instrument stopped working. It's a reasonable reconstruction, and it's how the event is remembered, but it isn't a measurement, and I'm not going to present it as one. The measured numbers alone put that storm at the top of anything recorded in the region, and they're bad enough. A sustained wind of 120 miles an hour is a strong hurricane arriving without an ocean underneath it. The damage in Tasiilaq was severe. Buildings were destroyed, roofs went, boats were wrecked, and the concrete result was institutional. Since 1970, the Danish Meteorological Institute has issued dedicated pittorak warnings for that coast, a specific product for a specific local hazard, which is the sort of thing that only gets created after a place teaches you a lesson. Pittoraks remain a regular feature of winter on the southeast coast. Strong events are quoted in ranges that would be extraordinary anywhere else, and they arrive with limited notice because the trigger conditions can assemble quickly. There's a related phenomenon that affects the sea more broadly, called barrier wind, and the mechanism is worth understanding because it explains why the winds along this coast so often run parallel to it rather than across it. When a weather system tries to push air toward Greenland from the east, the air runs into a 2-mile-high obstacle it cannot climb over easily, particularly when the air is cold and stably stratified and would need a lot of energy to be lifted, so it piles up against the slope instead. That piling raises the pressure along the coastal strip, and the resulting pressure gradient sets up a flow running along the barrier rather than over it. On the east coast of Greenland, that flow tends to run from the north toward the south, which is exactly the direction the current and the ice are already going. Down at Cape Farewell, where the barrier finally ends, the accelerated flow spills around the corner and forms narrow ribbons of extremely high wind reaching out into the Erminger Sea. Meteorologists call these tip jets. They can be a few tens of miles wide and hundreds of miles long, and they're strong enough to matter for the ocean underneath, which we'll come back to when we get to what happens to the water down there. Now stack all of this against the competition, because this is where the earlier claim gets its strongest support. The Labrador ice front does not have a 2-mile-high refrigerated dome sitting directly beside it. The Bering Sea does not. The Sea of Okhotsk does not. The Weddell Sea coast has Antarctic katabatic outflow, which is fierce, but the western Weddell pack is enormous and largely buffers the coastal wind effects from where ships actually operate, and there is no equivalent of a populated fjord coast being hit by 200-mile-an-hour drainage events. The East Greenland margin has all of it in one place, old thick ice arriving from upstream, a current that moves it fast and doesn't reverse, a lee shore with no refuge, polar lows forming at the ice edge where the work happens, and a mountain wall of ice generating some of the most violent surface winds in the hemisphere, aimed straight down the same fjords where the few settlements sit. That's the case for the title. And it's built on measurements rather than adjectives. But there's a further consequence of these winds that has nothing to do with sinking ships. And it turns out to be the single most important thing the Greenland Sea does for the rest of the planet. Wind blowing off a cold landmass over a cold ocean strips heat out of the water at a ferocious rate. Every hour that a katabatic outflow or a barrier wind runs across the open water of this sea, the ocean surface is losing heat to the atmosphere, and losing it fast. Water that loses heat gets denser. Water that gets dense enough sinks. Those two sentences are going to carry an enormous amount of weight before we're finished. First, though, there's the more immediate problem of what that same combination of cold air and open water does to anything floating on it. Seawater does not freeze at 32 degrees Fahrenheit. The dissolved salt gets in the way of the crystal structure, and ocean water of normal salinity stays liquid down to about 29 degrees. That 3-degree gap sounds trivial. It's the reason this sea can take a vessel apart without the vessel ever touching ice at all. Picture a boat working near the ice edge in winter. Air temperature well below freezing, say 0 Fahrenheit, which is unremarkable out there. Wind at 30 knots. Sea temperature just above its freezing point, so the water is liquid. Barely. The vessel is punching into a short, steep sea and throwing spray. Every droplet of that spray leaves the water at around 29 degrees and enters air at 0. In the time it spends flying, it cools. Some of it cools below its own freezing point without actually freezing, which liquids will happily do when there's nothing to nucleate on. And then it hits steel. Steel is a nucleation site and it's a heat sink. The droplet freezes on contact. The next one freezes on top of it. This is sea spray icing, and it is the dominant source of ice accretion on ships in cold waters. Freezing rain and freezing fog contribute, but spray does most of the work, because spray is generated continuously by the vessel's own motion. The boat is manufacturing its own hazard just by moving. The National Weather Service uses a threshold for heavy freezing spray of accumulation, faster than about 2 centimeters per hour, which is a bit under an inch. An inch an hour over everything. Now do the arithmetic, and I want to flag clearly that what follows is an illustrative estimate, rather than a measurement from a specific casualty. Ice weighs somewhere in the neighborhood of 55 to 60 pounds per cubic foot. Take a small working vessel with, say, 2,000 square feet of exposed surface once you count the wheelhouse, the masts, the rigging, the rails, the deck, and the gear. Coat all of it in 2 inches of ice. That's roughly 330 cubic feet of ice, which comes out somewhere around 9 or 10 tons. 10 tons is not the problem. Where the 10 tons sits is the problem. A vessel's stability depends on its center of gravity being low relative to its center of buoyancy. That's the whole reason ballast exists. Ice does not accumulate in the bilges where ballast belongs. It accumulates on the highest, most exposed, most wind-facing surfaces on the ship: the mast, the aerials, the wheelhouse roof, the upper rigging, the bow rails. You are effectively adding ballast to the top of the vessel, and you're doing it at the rate of an inch an hour, in the dark, while the sea state that generates the spray is also the sea state trying to roll you. Add to that the loss of freeboard as the whole vessel sits deeper, and free surface effects from water on deck that can no longer drain because the scuppers have frozen shut, and you have a boat whose righting ability is quietly being deleted, while the crew is fully occupied with everything else. Vessels have capsized from this while in no other trouble whatsoever. No collision, no grounding, no flooding from damage, no engine failure. Just a rising center of gravity in cold spray until the roll didn't come back. The most vulnerable designs are small vessels with large superstructures and low freeboard, which describes most of the fishing and sealing fleet that has ever worked cold water. There's a reason the historical casualty pattern in icing conditions is so heavily weighted toward boats of a certain size. What crews actually do about it is documented at length in mariner guidance and in National Weather Service material. And the honest thing to say here is that the response involves vessel-specific stability information, judgments about heading and speed relative to the sea, decisions about when to seek shelter, and physical removal of accumulated ice with mallets and bats and steam. Those decisions interlock, and a partial version of them would be worse than useless. So the complete procedure belongs where it lives, in official guidance and in the training of the people who do this for a living. The relevant point is why this hazard is worse on the East Greenland margin than it is in most cold seas. The ingredients are all present simultaneously and routinely. Very cold air pouring off an ice sheet, open water immediately adjacent to it because the current keeps a channel and the wind keeps opening leads, and sea states generated by systems that form right there. The Okhotsk and the Bering still produce more icing casualties because there are vastly more boats in them. Per vessel exposed, the East Greenland ice edge in winter is about as good at making ice on steel as any water on the planet. Then there's the water itself, and this is where the numbers get personal. At the ice edge in the Greenland Sea, the surface water is sitting close to its freezing point, in the high 20s Fahrenheit. Somebody who goes into that water is not on a clock that runs in hours. The first thing that happens is cold shock, and it happens within seconds. The body responds to sudden cold immersion with an involuntary gasp, followed by uncontrollable hyperventilation. If the gasp happens underwater, the sequence can end right there. The hyperventilation peaks in the first minute or so, and then eases. And that first minute is where a large share of cold water deaths actually occur, long before body temperature has dropped meaningfully. If someone gets through cold shock, the next phase is incapacitation. Cold water pulls heat out of the limbs fast, nerve conduction slows, muscles stop responding, and manual dexterity goes first. Within roughly 10 minutes in near-freezing water, most people can no longer perform useful physical work, including gripping a line thrown to them or operating the latch on a life raft. Swim failure follows, hypothermia, the thing everyone names, comes third and takes longer. The old survival tables that told people they had 30 or 45 minutes in freezing water were describing when core temperature might become critical, and they've been criticized precisely because they gave the wrong impression of the timeline. Drowning from incapacitation usually gets there first. This is why immersion suits exist, and why their use on cold water vessels is not optional under modern rules. It's also why the practical rescue window in a place like this is measured in the time it takes for somebody nearby to reach you, and why the nearest somebody being 300 miles away changes the meaning of every other risk on the vessel, which raises the question of who's out there to reach you and how anybody knows where the ice is in the first place. There's a document type that governs almost everything that happens on this water, and outside the profession almost nobody has ever seen one. It's called an ice chart. The Danish Meteorological Institute produces them for Greenland waters, the Norwegian Ice Service produces them for the Svalbard side and the Greenland Sea. Canada, Russia, and the United States run their own for their own waters. These are operational products, published on a schedule, and if you are taking a vessel anywhere near this ice, you are reading one before you go, and you are reading the updates while you're out there. For most of the 20th century, an ice chart was assembled out of ship reports and aircraft reconnaissance. Somebody flew, somebody looked, somebody drew. That method produces excellent detail along the flight line and nothing at all anywhere else. And it fails completely in fog, which is abundant here. Now, the primary input is satellite radar. Radar imaging from orbit works through cloud and through darkness, which in a place with months of polar night and near-permanent low cloud is the whole reason it's usable. The radar return from open water, from thin new ice, from thick first-year ice, and from old multi-year ice differs, because the surfaces have different roughness and different salt content, and that difference is what an analyst reads. And it is still an analyst. Automated classification has improved substantially, but the operational charts for these waters are drawn by human ice analysts looking at imagery, because the ambiguities are the kind that require judgment. Wet ice in summer can look like open water. Rough open water in a strong wind can look like ice. Melt ponds confuse everything. What comes out is a map covered in ovals, and the ovals are where the real information lives. The system is called the egg code, because the ovals look like eggs, and it's an international standard. Inside each oval is a small stack of numbers. The top number is total ice concentration, expressed in tenths rather than percent. So a 9 means 9/10 of the sea surface. Within that polygon is covered. Below that, up to 3 ice types are described separately. What fraction of the total each one is, what stage of development it's at, meaning roughly how old and therefore how thick and what size the flows are. Once you can read it, a single oval tells you this area is 9/10 covered. 6/10 of it is thick first-year ice, 2/10 is old multi-year ice, 1/10 is new ice, and the flows run from small to medium. That is an enormous amount of operational information in a symbol the size of a thumbnail. And the reason it's structured that way is that those distinctions decide whether a given ship can proceed. 2/10 of old ice in an otherwise navigable field is not a minor footnote. Old ice is the stuff that holes hulls, and a vessel without the right ice class has no business in that polygon regardless of how open the rest of it looks. The honest limitation is a big one. An ice chart has a valid time, and the ice does not respect it. The pack in this current moves 5 to 25 miles a day. A chart issued this morning based on a satellite pass from last night describes a distribution that has already moved by the time it reaches the bridge. Add a strong wind event, and the whole edge can shift dozens of miles in a day. Charts are indispensable, and they are always, structurally, describing the recent past. They also don't reliably show the small killers. An iceberg large enough to matter shows up. A growler riding low with a few square feet above the surface pounds does not appear on a chart drawn at that scale, and it can be difficult to pick out on ship's radar in a seaway, because the sea clutter hides it. So the chart tells you where the pack is. It does not tell you what's floating in the 50 miles of open water in front of it. Which brings up the thing that surprises people most about ice edges. There isn't a line. On a map, the ice edge is drawn as a boundary, and that makes it look like a coastline. In reality, there's a transition region called the marginal ice zone, where concentration falls off from the solid pack to open water. It can be a couple of miles wide when conditions are calm, or well over 100 miles wide when a storm has been working on it. Off East Greenland, the drift ice belt is often broad enough that a vessel can spend the better part of a day crossing it. And this transition zone is where the ocean and the ice fight each other in a way that produces a piece of physics I find close to elegant. Ocean swell arriving from the open Atlantic doesn't stop at the ice. It propagates into the pack, flexing the flows as it passes underneath them. The ice resists, absorbs energy, and the wave amplitude decays with distance into the pack. That's why heavy ice is such effective protection. Get far enough in, and the sea goes flat, which is the oldest reason in the book for a small vessel to seek the ice rather than avoid it in bad weather. But the flexing works both ways. A large floe being bent repeatedly by swell will eventually fracture, because ice is strong in compression and weak in bending. So the swell breaks the big floes into smaller ones, and smaller floes flex less and survive better. And the result is a natural size gradient. Deep in the pack, floes are large. Near the edge, they're small and getting smaller. In a big storm, observations have recorded swell breaking up ice far into what was solid pack the day before. That gradient is exactly why the outer edge of this drift ice belt is such an unpleasant place to be. You've got substantial waves and you've got ice simultaneously, and a flow several feet thick with a few tons of mass, lifted on a swell, is not an obstacle you steer around at leisure. It's a moving object with momentum, and so is the one behind it. Deep in the pack, you have ice and no waves. Outside the belt, you have waves and no ice. The band in between has both, and every vessel that works this margin has to cross it in each direction. There's one more thing that happens in that band, and it sets up the strangest behavior this sea has. When seawater starts to freeze in water that's being agitated by waves, it can't form a smooth sheet. The first ice crystals, called frazzle, are tiny needles and platelets suspended in the top few feet. And the turbulence keeps stirring them, so they never get to settle into a continuous layer. The water turns into a gray soup with the consistency of a slush drink. As it thickens, the soup congeals into rounded lumps, and those lumps bump into each other constantly in the swell, so their edges get pushed up into raised rims. The result is called pancake ice, and it looks exactly like the name. A field of pale discs, a foot to 10 feet across, each with a slightly upturned lip, packed edge to the horizon, all of it rising and falling with the swell. It is a beautiful thing to look at, and in the Greenland Sea it used to be the visible signature of a process happening underneath it that almost nowhere else on Earth performs. Around 72 to 74 degrees north, a branch of the East Greenland Current peels away from the coast and turns east out into the middle of the sea, heading roughly toward the island of Jan Mayen. It's called the Jan Mayen Current, and it carries cold, low-salinity polar water away from Greenland and into open ocean. In the 1980s and 1990s, in winter, that eastward tongue of cold water did something spectacular. It grew its own ice. Nothing about this was imported from the Arctic. This was new ice, forming in place, on water that had been open the week before. It would start along the eastern flank of the existing pack, spread east over the cold water of the Jan Mayen Current, and build a great tongue of new ice, reaching out into the Greenland Sea, sometimes for hundreds of miles, while leaving a bay of open water enclosed behind it to the northwest. The Norwegians named the tongue the Odden, which means the point or the headland, because on a chart it stuck out like a cape. The bay it enclosed was the Nordbukta, the North Bay. In the winters, when it formed strongly, the Odden covered an area estimated in the hundreds of thousands of square kilometers, comfortably over 100,000 square miles. And then, in a matter of days, it could largely vanish and reform. It was not a stable feature that grew through the season and melted in spring. It pulsed, appearing and disappearing several times in a single winter, tracking the weather. Most of it was pancake ice, millions of those pale-rimmed disks, growing in agitated water packed together across an area the size of a large state, rising and falling on Atlantic swell. If you're wondering why oceanographers cared enormously about a temporary patch of slush in the middle of nowhere, the answer is the hinge this entire sea turns on. When seawater freezes, the salt does not go into the ice. Ice crystals form from water molecules, and the dissolved salt gets excluded and concentrated into the remaining liquid. Some of it is trapped in brine pockets inside the ice, but a large share is rejected downward into the water directly below the freezing surface. That rejected brine is intensely salty and extremely cold. Salty cold water is dense water. It's the densest water anybody makes anywhere at the ocean surface. So a field of new ice, forming rapidly over open ocean, is a machine for injecting dense water into the layer beneath it. Every square mile of the Odden that froze was pumping brine downward. Now consider where that machine was sitting. The middle of the Greenland Sea is occupied by a slow counterclockwise circulation called the Greenland Sea Gyre. In a rotating gyre of that sense in the northern hemisphere, the density surfaces in the interior get pulled upward toward the center, a shape oceanographers call doming. What that means in practice is that in the center of this gyre, cold, dense water that would normally be sitting a mile down is already close to the surface. The water column there is unusually weakly stratified. There's very little density difference between the layers, which is exactly the condition under which a column becomes easy to overturn. Put a brine factory on top of a weakly stratified column, and you get one of the very few places on this planet where the surface of the ocean can sink all the way to the bottom. Take that literally, because the measurements do. In the winter of 1971, oceanographers sampling the center of the Greenland Sea found an oxygen-rich, nearly uniform layer of water extending from the surface all the way down to around 11,500 feet. Uniform, meaning the water at the surface and the water 2 miles down had effectively the same properties because the whole column had been mixed. Think about what that requires. A patch of ocean cooling and densifying at the surface until it becomes heavier than everything beneath it, and then falling in plumes, kilometers deep, dragging surface water and the oxygen and the carbon dioxide dissolved in it down to the seafloor. There are only a handful of places on Earth where this happens at all. The Labrador Sea does a version of it. Parts of the Mediterranean do a shallower version. Around Antarctica, the Weddell and Ross Sea shelves do the deepest version. And the Greenland Sea in the right winter does it too. And it does it faster and more locally than almost anywhere. The individual plumes have a name that fits: chimneys. Narrow columns, perhaps 6 to 12 miles across where the surface water actually descends. From above, in the right conditions, they can show up as patches where the ice fails to form because sinking water is being replaced by slightly warmer water from below. Now the part that matters. The Aden stopped showing up. Through the 1990s, the ice edge in this region retreated westward, and the tongue appeared less often and less strongly. Since around the turn of the century, the central Greenland Sea has been largely ice-free through the winter, and the Aden, as a regular feature, has essentially gone, and the convection changed with it. That homogeneous column down to 11,500 feet in 1971 has not been repeated. Since the late 1970s, wintertime convection in the Greenland Sea has generally been observed reaching intermediate depths rather than the full water column, typically less than about 6,500 feet and often much less. The deep water at the bottom of the basin no longer gets renewed from above the way it did. What the process mostly produces now is an intermediate layer part-way down. The explanations researchers give involve several factors acting together. Less ice formation means less brine, so less densification at the surface. Weaker wind forcing over the gyre means less doming, so a more stratified column that's harder to break, and the amount of heat the atmosphere pulls out of this sea appears to have declined measurably since the end of the 1970s, on the order of a fifth. Each of those is a piece, and I want to be careful not to present the combination as more settled than it is. The precise weighting between them remains an active argument in the literature, and the system varies naturally on decade timescales in ways that make single-event attribution difficult. What is not in dispute is the observation. The deepest convection in the Greenland Sea was measured. It was measured again for decades afterward, and it does not reach the bottom the way it once did. To understand why that matters far beyond this sea, you have to know what the sinking connects to. The Atlantic Ocean runs a circulation that behaves something like a very slow, very large heat pump. Warm, salty water travels north near the surface, from the tropics up past the eastern United States, across toward Europe, and on into the seas north of Iceland. Along the way, it gives up heat to the atmosphere, an enormous amount of heat. The northward heat transport of the Atlantic overturning circulation, measured by an array of moorings strung across the ocean at about 26 degrees north, runs somewhere in the neighborhood of 1.25 petawatts. That unit is close to meaningless without a comparison, so here's one. Total human energy consumption, everything, every power plant and vehicle and furnace on Earth, averages somewhere around 19 terawatts. The Atlantic carries roughly 70 times that much heat northward, continuously, as a side effect of water moving. That heat is why Bergen, Norway, at 60 degrees north, has winters that a resident of Winnipeg at 50 degrees north would consider mild. Latitude alone would predict something far harsher for Northwest Europe than what actually happens there. Now that heat pump has to return. Water going north at the surface has to come back south at depth. And the way it gets to depth is by sinking. And the sinking happens in a small number of places. And one of them is the sea we've been following. Water that cools in the Nordic seas becomes dense enough to descend and pool in the deep basins. The Greenland Sea Basin, at nearly 16,000 feet, is one of those reservoirs. So is the Norwegian Sea Basin. Cold, dense water accumulates there, and then it runs into a wall. Between Greenland and Scotland, by way of Iceland and the Faroe Islands, there's a submarine ridge. It's a genuine topographic barrier, a raised rim separating the deep Nordic seas from the deep North Atlantic, and dense water sitting in the Nordic basins cannot simply flow south along the bottom, because the bottom rises up in front of it. There are only a few notches in that rim. The Faroe Bank Channel is the deepest, at around 2,700 feet. The Iceland-Faroe Ridge is shallower, and the Denmark Strait between Greenland and Iceland has a sill at roughly 2,000 feet. That last one is where the Greenland Sea's cold water gets out, and what happens there is, by any reasonable accounting, the largest waterfall on this planet. Dense water pooled behind the sill spills over it and immediately encounters the continental slope on the far side, dropping away toward the Erminger Basin. Being much denser than the water around it, it stays on the bottom and runs downhill, plunging roughly 11,500 feet from the sill to the deep basin below. The volume going over is close to 3¼ Sverdrups, which comes out around 3¼ million cubic meters every second. Estimates from moored instruments across the strait, covering roughly 2 decades, put the mean at about that value, with an uncertainty of half a Sverdrup or so. The comparison people usually reach for is Niagara Falls, which averages somewhere around 2,400 cubic meters per second. The Denmark Strait overflow moves more than 1,000 times that. If you prefer rivers, the Amazon discharges roughly 200,000 cubic meters per second at its mouth, which makes this cataract something like 15 Amazons, going over a drop more than 3 times the height of Angel Falls, entirely underwater, invisible from the surface, running continuously. The physics of it is less like a waterfall and more like an avalanche, which is the more accurate picture. Water doesn't free fall through water. What you have is a dense gravity current hugging the seabed, accelerating down the slope, turbulent along its upper boundary where it drags in and mixes with the lighter water above it. By the time it reaches the deep Erminger Basin, it has entrained so much ambient water that the flow has grown substantially beyond what crossed the sill. That mixture, joined by the overflows through the other notches in the ridge and by water that sinks in the Labrador Sea, becomes North Atlantic deep water, and it heads south along the western side of the Atlantic at depth. It takes centuries to make the journey. Some of it reaches the Southern Ocean and gets folded into the circulation around Antarctica, and the whole thing eventually returns to the surface somewhere, decades or centuries later, and starts again. So the chain, laid out cleanly, cold wind pours off the Greenland ice sheet and off the ice pack, strips heat from the surface of the Greenland Sea, ice formation rejects brine and adds salt. The water becomes dense. It sinks in a gyre that's already primed for it. It fills the deep basin, and it eventually escapes over a sill and cascades into the Atlantic, where it becomes the return leg of the circulation that keeps northwestern Europe habitable at latitudes that have no business being habitable. Every step of that is measured. None of it requires you to take anyone's word. Now the correction, because there's a version of this story that gets told too simply, and the simple version fails the moment you look at the source water. The dense water going over the Denmark Strait sill is not purely Greenland Sea product. Work over the last 2 decades has shown the overflow draws on several sources: water formed in the Greenland Sea, water from the Iceland Sea, water that came south through Fram Strait from the Arctic, and Atlantic water that circulated around the Nordic seas and densified along the way. A current running westward along the North Icelandic slope, identified relatively recently, turns out to supply a substantial share of it. The Greenland Sea is a contributor to the overflow. Calling it the source would be tidier, and it would be wrong. And there's one observation that badly complicates the alarming version of this story, which I think has to be stated, because leaving it out would be a form of lying by omission. Across roughly 2 decades of continuous mooring measurements, the transport through the Denmark Strait has shown no clear trend. The overflow has kept running at essentially the same rate through a period in which Greenland Sea deep convection weakened substantially, Arctic sea ice declined, and the Greenland ice sheet lost mass at an accelerating rate. That does not mean the system is invulnerable. It means the plumbing has more redundancy in it than the simple picture implies, that source waters can substitute for one another, and that anybody claiming to know exactly where the tipping point sits is claiming more than the measurement support. What we do know is where the pressure is being applied, and it comes back to the thing this whole coast delivers. Every flow drifting south along the Greenland coast is a delivery of fresh water in solid form. That's worth stopping on, because it's the least obvious property of sea ice, and it's the one with the longest reach. Old multi-year ice has had its brine flushed out over successive summers. By the time a flow has survived a few melt seasons, its salinity has dropped to a small fraction of the ocean's, and some of it is nearly fresh enough to drink. Whalers and expedition crews used old flow ice for drinking water routinely, and picking the right ice was a practical skill. So when the Arctic pushes roughly 500 cubic miles of ice a year down this coast, it is also pushing 500 cubic miles of fresh water down this coast, packaged so that it doesn't mix into the ocean until it melts. And it doesn't melt until it gets south. On top of that solid delivery, there's a liquid one. The polar surface layer riding on the East Greenland current is markedly fresher than Atlantic water, because it's the outflow of an Arctic Ocean fed by the enormous Siberian and Canadian rivers, by Pacific water coming in through the Bering Strait, and by melt. Oceanographers express this as a freshwater transport, which is a slightly abstract quantity. It's how much pure fresh water you'd have to add to a reference salinity to produce the observed water. In the East Greenland current, that figure has been estimated in the range of 80 to 130,000 cubic meters per second. Set that against the Mississippi at around 16,000 cubic meters per second, and this current is carrying a freshwater load equivalent to something like 5 to 8 Mississippi rivers at the surface, headed south. On top of denser water it refuses to mix with. More than 30% of the total oceanic freshwater transport crossing the gap between Greenland and Scotland travels in the coastal current on this side. That number and the business of sinking are on a collision course, and the reason is almost embarrassingly simple. Sinking requires dense surface water. Dense surface water requires cold and salt. Fresh water at the surface is light. It floats, and it will keep floating no matter how cold it gets, because below about the freezing point it just turns into ice. A layer of fresh water at the top of the ocean acts as a lid. Cool it as hard as you like, blast it with katabatic wind all winter, and if it's fresh enough, it will not become dense enough to sink through the saltier water underneath. So the same current that makes this the most hostile ice margin in the north is also the one delivering the substance most capable of switching off the sinking that happens beside it. We've watched this happen, at least partially, and there's a name for it. Starting in the late 1960s, an enormous body of unusually fresh water appeared in the northern North Atlantic and then traveled around the subpolar gyre over the following decade and a half. It showed up off East Greenland, moved around Cape Farewell into the Labrador Sea in the early 1970s, crossed the Atlantic, and eventually returned to the Nordic seas by the early 1980s. Oceanographers call it the Great Salinity Anomaly, and the leading explanation traces it to a large export of sea ice and fresh polar water through Fram Strait in the late 1960s. The effect was measurable, and it was exactly what the physics predicts. Where that fresh cap arrived, convection weakened. In the Labrador Sea, deep winter mixing was suppressed for years while the anomaly was overhead, and then it resumed after the anomaly passed. Further freshening events followed in the 1980s and again in the 1990s, and recent work has connected the loss of the Auden ice tongue to those anomalies and to related changes in Labrador sea ice, which would make the two convection sites in the Northern Hemisphere participants in the same story, rather than independent systems. I'll flag the uncertainty honestly because it's real. The origin of the first Great Salinity Anomaly has been debated for decades. An alternative or contributing explanations involve atmospheric forcing patterns and changes in the Nordic seas themselves. What the record establishes beyond argument is the sequence. A fresh anomaly moved through, and where it moved through, sinking stopped. The traverse still owes us an ending, though, because the ice has to stop being ice somewhere. South of the Greenland Sea proper, the drift ice belt continues down the coast. It has a name in Greenlandic waters that everybody who works there uses, the Storis, meaning the Great Ice, and it is specifically the old Arctic pack that came down the east coast rather than anything grown locally. By the time the Storis reaches the southern tip of Greenland, the flows have been worn down. Measurements in the Cape Farewell region find flows that are almost always under 300 feet across, which is small by Arctic standards. But their thickness is still 6 to 10 feet, and thickness is what matters when something hits your hull. Cape Farewell itself is a serious piece of water, for reasons that involve no ice at all. This is where the barrier winds running down Greenland's coast reach the end of the barrier and spill around the corner, forming those narrow ribbons of extreme wind. It's a cape with a reputation among sailors that it has earned repeatedly, and vessels crossing between Greenland and Europe routinely stand 100 miles or more offshore, rather than cutting the corner, precisely because the ice and the wind are both concentrated there. The ice that rounds the cape gets picked up by the West Greenland Current and turned north, up the other side of the island. In an average year, the Storis pushes north of about 63 degrees, into the fishing grounds off Nuuk, roughly every other season. Some years it's a few narrow belts that pass in days. Other years it's a broad field that sits there for weeks, closing harbors on a coast that expects to be open. And then it melts. Somewhere in the Erminger Sea, somewhere in the northern Labrador Sea, somewhere off the fishing banks of West Greenland, flows that formed north of Siberia 5 or 6 years earlier and crossed the top of the world finally disappear, and everything they were carrying goes into the water. Look at where that happens on a chart, and the significance is hard to miss. The ice ends its life directly on top of the other place in the northern hemisphere where the ocean sinks. Treat this margin purely as a machine for destroying things, and you get an accurate account of what it does to steel and a badly incomplete account of the place. Because the same conditions that make it lethal to a ship make it extraordinarily productive for everything that lives here. Start with the deep mixing, because the biology follows straight out of it. When a water column overturns in winter, it doesn't only carry surface water down. It carries deep water up. Nutrients that have been slowly accumulating at depth for years, nitrate and phosphate and silicate that sank with dead organisms and got remineralized in the dark, get lifted back into the sunlit layer. Deep convection is a nutrient pump running in reverse of the biological one, and a sea that mixes deeply in winter starts the spring with a full tank. Then the light returns, and the ice edge does something specific. As the drift ice belt retreats and breaks up in spring, the melting flows release fresh water at the surface. Fresh water is light, so it forms a shallow, stable layer. And a shallow, stable layer is exactly what a phytoplankton bloom needs. Plankton in a deeply mixed column spend most of their time below the depth where there's enough light to grow. Cap the column with a thin, buoyant lid, and suddenly they're held in the light all day, with nutrients underneath them that the winter delivered. The result is a bloom that tracks the retreating ice edge like a wave, moving north and west across the Greenland Sea through the spring and early summer, following the melt. Underneath the ice itself, there's a second system that most people never picture. The bottom few inches of a sea ice floe are not solid. They're a porous matrix of ice crystals threaded with channels of brine, and that matrix is habitat. Specialized algae live in it, gathering what little light penetrates the floe and the snow on top of it, and they bloom earlier in the year than anything in the open water can, because they're already positioned in the light while the water below is still dark. Brown and gold streaks on the underside of a floe, visible when a chunk flips over, are those communities. Ice algae start the food web weeks before the open water bloom does, and the timing matters enormously. Grazers that depend on that early production have life cycles synchronized to it. The animal that ties the whole system together is a fish about the length of your hand. Polar cod live in and around the ice, sheltering in cracks and underflows, and they're the crucial link between the plankton and everything with a backbone. Seals eat them. Seabirds eat them. Beluga and narwhal eat them. In terms of energy transfer, a very large share of the Arctic marine food web routes through this one species, which means a change in how much ice there is, and when, propagates upward through everything. Then there are the openings in the ice, which turn out to be as important as the ice. A polynya is a persistent area of open water surrounded by ice, and there are two ways to make one. The first is mechanical. Wind or current pushes ice away from a fixed boundary faster than new ice can form, so the water stays open by being continuously swept clear. Those are the ones the offshore katabatic winds of East Greenland produce along the coast, and it's a neat inversion because the same wind that makes the coast dangerous for humans keeps water open that a great many animals depend on. The second kind is thermal. Warmer water reaching the surface from below prevents freezing. On the northeast Greenland shelf, near the top of the coast, there's a large recurring one known as the Northeast Water Polynya, opening in a region that's otherwise locked. Places like that are disproportionately important. In a landscape sealed under ice, an area of reliable open water is where air-breathing animals can breathe, and where light can reach the water, and the biology concentrates there in numbers that look implausible against the surrounding emptiness. Walrus haul out on the ice over the shallow banks off northeast Greenland, because walrus feed on clams and other bottom animals, and need water shallow enough to reach the seabed with ice nearby to rest on. Belgica Bank provides exactly that combination, and the walrus that use it are an unusually isolated population. Ringed seals live under the fast ice along the coast, maintaining breathing holes through ice several feet thick by scraping with the claws on their foreflippers and building layers in the snow drifts above those holes where they give birth. It's a life spent almost entirely on the ice side of the boundary, and it requires ice that stays put long enough to hold a lair through a pupping season. Polar bears follow the ringed seals because ringed seals are the primary prey across most of the bear's range. And the East Greenland bears are a distinct subpopulation that hunts the drift ice belt. Harp and hooded seals use the drift ice out in the west ice, whelping in enormous concentrations in March and April on floes that will be 100 miles from where they started by the time the pups are weaned. And then there's the whale that gave this sea its economic history. The bowhead is a slow, enormously heavy, ice-adapted whale with a skull built to break through ice from below in order to breathe. Old English sources call it the Greenland right whale, and the word right in that name is a commercial judgment. It was the right whale to kill because it was slow. It carried extraordinary quantities of oil and baleen, and it floated after death instead of sinking. The Spitsbergen bowhead fishery opened in the early 1600s and ran, in various forms and by various nations, for something over 2 centuries. It was worked out of the waters between Svalbard and Greenland, in exactly the ice margin this whole traverse has followed. At its height, it was a major European industry, with shore stations, fleets, and a scale of killing that reduced the stock to a remnant. That population has never recovered to anything like its former numbers. Modern estimates for the bowheads of the Svalbard and East Greenland region run in the hundreds rather than the tens of thousands the fishery implies, though sightings in recent years have been more frequent than researchers expected, and there's cautious evidence the remnant is slowly increasing. So the honest picture of this margin is a place that kills machinery and supports life in abundance. And those two facts are not in tension. They're the same physics viewed from different positions. Cold, moving, brine-loaded, seasonally lit water is exceptionally hard on ships and exceptionally good at growing things. The people who have lived on this coast worked that out a very long time before anyone wrote it down. The east coast of Greenland is called Tunu in Greenlandic, which translates roughly as the backside, and the people of that coast are the Tunumiat. They speak Tunumiasit, an East Greenlandic dialect different enough from the West Greenlandic that the country uses as its official language that speakers of one can struggle with the other. That linguistic distance is a direct measurement of what the ice does. Greenland's population has always been concentrated on the west coast, where the West Greenland current brings comparatively mild water north and where harbors work for most of the year. The east coast, sitting under the outflow of the Arctic Ocean, was cut off. The Storis made coastal travel between the two sides difficult and seasonal, and it made contact with Europe rarer still. A community can drift linguistically over centuries when the sea between it and everyone else is full of ice for most of the year. The scale of that isolation showed up in 1884. A Danish expedition led by Gustav Holm set out to travel up the east coast from the south, and they made a decision that tells you something about the intelligence of the plan. They left the European vessel out of it. They traveled in umiaks, the large open-skin boats used by Greenlandic families, with Greenlandic crews. Small draft, light, able to be hauled out over ice and carried around obstacles. The right tool, borrowed from the people who developed it for exactly this coast. They reached the Ammassalik district and found a community of somewhere around 400 people who had effectively no direct contact with Europeans. It's important to say what that does and does not mean, because this is where a certain kind of documentary reaches for words like untouched and timeless, and those words are wrong. The Tunumiat were not unaware that a wider world existed. Goods and information moved along the coast and around the southern tip through trade, slowly. What they had was geographic isolation enforced by ice, in a place where their technology and knowledge worked and European technology did not. Holm's expedition succeeded because it adopted the local method. A trading and mission station was established at Ammassalik about a decade later, and that settlement grew into Tasiilaq, which today has around 2,000 people and is the largest town on the entire east coast of Greenland. 2,000 people on a coastline over 1,000 miles long. Supply reaches Tasiilaq by ship from around the end of May until the beginning of December. Roughly 6 months of maritime access and 6 months without. Then there's the other town. In 1925, families from the Ammassalik district, along with some from the west coast, were moved north to found a settlement at the mouth of one of the largest fjord systems on Earth, in central East Greenland. The project was organized with the involvement of Einar Mikkelsen, the same man who had spent 3 years marooned on Shannon Island a decade and a half earlier. And the motives were mixed. Hunting grounds in the new district were rich, and Denmark had an interest in establishing settlement to support its claim to the coast. The town is Ida Korturmit. Today it has somewhere around 350 residents, down from more than 502 decades ago. The supply ship comes twice a year, once in July, once in September. Think about the logistics that implies. Everything that arrives by sea for a full year arrives in 2 deliveries during one short window. For roughly 9 months, the food in the shop comes out of storage and freezers stocked the previous autumn. Fuel for the year comes in on those ships. Building materials come in on those ships. Air access exists by helicopter and small aircraft on a limited schedule, and it's expensive and weather-dependent. And the weather on that coast is the Pitarack coast weather, which does not negotiate. And in October of 2020, the supply ship serving that town got stuck in the ice in front of it for 2 days. Now, the part that gets left out of most accounts of places like this, and getting it wrong, is the difference between a documentary and a postcard. The sea ice off that coast is not primarily an obstacle to the people who live there. It's the road. For roughly 9 months of the year, the fast ice along the coast and in the fjords is a travel surface. Dog sledge and snowmobile move across it to hunting grounds, to fishing spots, between settlements, to places that in summer would require a boat and a long detour. Hunters work from the ice edge, where seals and narwhal come to breathe. Halibut are fished through holes cut in the ice. The ice is where the economy happens, which means that when people on this coast talk about sea ice changing, they're talking about their infrastructure, not their scenery. Freeze up arriving later and break up arriving earlier compresses the season when travel is possible. Ice that forms thinner or more irregularly is ice you can't trust with a sledge and a team, and the local knowledge that tells you where and when the ice is safe was built on a pattern that's shifting under it. Hunters in East Greenland have described exactly this: routes their fathers used that no longer hold, seasons that no longer arrive on schedule, decisions that used to be routine and now carry risk. The population decline in Itakortormiit tracks the same pressures that empty rural communities everywhere, and it would be a mistake to read it as a story purely about ice. Young people leave for education and jobs. Services concentrate in larger towns. The cost of living where everything arrives twice a year is punishing. Hunting quotas and international restrictions on products from marine mammals have hit the traditional economy hard. What I'd push back on is the framing that treats these communities as evidence of the environment's hostility, as though people living there is somehow an anomaly requiring explanation. People live there because their families have lived there, because the hunting is good, because it's home, and because the coast supports a way of life that works when you know it. The remoteness is a fact about the rest of us, measured from where we happen to be standing. Nobody in Itakortormiit thinks of Itakortormiit as remote. There's a tourism industry now, small and growing, built around exactly the things that made this coast impassable: the ice, the wildlife, the fjords. Vessels come north in summer. That brings money, and it brings a different set of risks, because a cruise ship in the East Greenland ice is a very large number of people in a place where help is a very long way away, which is the last operational question this coast raises. If something goes wrong out there now, in the era of satellites and ice charts and helicopters, who actually comes? Search and rescue across Greenland and the waters around it is the responsibility of the Danish Joint Arctic Command, headquartered in Nuuk on the west coast. Its area covers an island the size of Western Europe plus the ocean around it, and it does that with a small number of naval vessels, a couple of long-range surveillance aircraft, contracted helicopters, and cooperation agreements with neighbors. Look at where the assets are and the geometry of the problem becomes obvious. Nuuk is on the west coast. The airfields are mostly on the west coast. On the east coast, north of Tasiilaq, there's an airstrip serving Itakortormiit, and beyond that, at 81.5 degrees north, a small military station near the top of the island. Between those points lie hundreds of miles of coast, with nothing. A helicopter has a radius, and the radius is not negotiable. A vessel in difficulty 500 miles up the northeast Greenland coast in November is not within helicopter range of anything, and the nearest ship capable of operating in that ice may be a very long way off and may itself need days to get there through the ice that caused the problem. Distance to help is the measure that quietly turns manageable incidents into serious ones. Everywhere else on the list of competing ice margins, there's someone within a plausible response time. Off northeast Greenland in winter, there frequently is not. The international rules acknowledge this in a way I find quietly chilling once you understand what it implies. Since 2017, ships operating in polar waters have been governed by a mandatory code produced through the International Maritime Organization, generally just called the Polar Code. It requires a lot of sensible things: an operational manual specific to the vessel and its ice capability, a stated ice class, trained and certified ice navigators, equipment rated for the temperatures actually expected, procedures for operating in the presence of ice. And it requires that survival equipment aboard be sufficient for the maximum expected time of rescue, with an absolute minimum of 5 days. 5 days. That number exists because somebody sat down and worked out realistically how long people might be sitting on the ice or in a lifeboat in these waters before anyone reaches them, and 5 days was judged the floor, not the worst case. Compare that with any other maritime environment. In the North Sea, in the Gulf of Mexico, in the Mediterranean, a well-equipped rescue response is measured in hours. The Polar Code also sorts vessels into categories according to what ice they're permitted to enter, and above that sits the ice class system, which runs from the highest polar classes, meant for year-round operation in thick multi-year ice, down through classes suitable only for thin first-year ice in summer. Those classes describe hull strengthening, frame spacing, plate thickness, propeller and shaft design, machinery power, and the ability to keep going astern in ice. A ship's ice class is a legal and engineering statement about which of those egg code polygons it may enter, and the East Greenland margin routinely contains polygons that exclude almost everything afloat. There's an older form of presence on that coast that has nothing to do with ships at all. The Danish military maintains a unit called the Sirius Patrol, which operates in the Northeast Greenland National Park, and it patrols by dog sledge. Not as a ceremonial exercise, as the actual operational method, because dog teams work in terrain and conditions where vehicles do not, and because the distances and the absence of infrastructure make anything else impractical for months at a time. Members serve in pairs, posted for around 2 years, and a patrol pair with a team of dogs may cover thousands of miles over a season, sleeping in a tent, resupplying at depots and old trapper huts scattered along the coast, out of contact for long stretches. It's the only military dog sledge patrol in the world, and it exists because that coast has not yet been solved by technology. Then there are the scientists, and their operations tell you something about how the balance has shifted. The Fram Strait moorings have to be serviced annually, and that means a research vessel goes to a specific point in one of the harder pieces of water in the hemisphere, on a schedule, every year, and comes back. Purpose-built polar research ships now do this routinely. Some of them can work through the winter, which for most of the 20th century would have been unthinkable outside of a deliberate drift like the Frams. And increasingly, the instruments do the waiting instead of people. Buoys are frozen into flows deliberately and transmit position, ice thickness, temperature, and weather by satellite as they drift the same route the Jeannette's wreckage took. Autonomous underwater gliders profile the water column and surface to call home. Moored sonars, Nordsonar, listen upward through the dark for years at a time. The consequence is that a sea which could hide a 5-ship disaster in 1952, leaving nothing at all to find, is now observed more or less continuously. What I take from all of that is the thing that changes how the word hostile should sit in your head. None of this made the Greenland Sea gentler. The ice is still arriving through Fram Strait in the same quantities. The pitteracks still come down the fjords. The polar lows still spin up off the ice edge in 6 hours, and the water is still cold enough to incapacitate a person in 10 minutes. Every physical fact about that water remains exactly as true as it was when the Hansa's crew were building a house out of coal bricks. What changed is that the mechanisms are known. The wind has a mechanism. The ice has a source and a speed. The storms have an ingredient list. The water has a measured freezing point and a measured effect on a human body. Every one of those was, at some point, discovered by somebody who did not know it and paid for the lesson. That's what informed respect actually looks like, and it's a better response to a place like this than dread. Dread makes you avoid a thing. Understanding lets you work in it, with your eyes open, carrying 5 days of survival gear because somebody did the arithmetic on how long you might be out there. Which leaves one question: why should any of this matter to somebody who will never see it? The answer has 3 parts, and all 3 of them are physical, not sentimental. The first is heat. The circulation that carries that petawatt scale, heat load north across the Atlantic, depends on water coming back south at depth. And the water comes back south at depth because it sinks in a handful of small regions at high latitude. The Greenland Sea is one of them. If you live anywhere in northwestern Europe, the reason your winters resemble the winters of a place 1,000 miles closer to the equator involves what happens in this sea and the seas beside it. If you live on the eastern seaboard of the United States, the same circulation runs past you on its way north, and shifts in it show up in your sea level and your fisheries. The second is carbon. Ocean water absorbs carbon dioxide from the air, and surface water that gets carried down into the deep ocean takes that dissolved carbon with it, where it stays for centuries, because that's how long it takes for deep water to come back up. Convection is the mechanism that does the carrying. Estimates of where the ocean's inventory of human-emitted carbon actually sits put a disproportionate share in the North Atlantic and the seas north of it, far out of proportion to their area, precisely because this is where the surface goes down. Whatever share of our emissions the ocean has quietly absorbed, a meaningful part of it went underwater through places like this one. The third is oxygen, and it's the least discussed. The deep water in the Greenland Basin, nearly 3 miles down, is oxygen-rich. And it's oxygen-rich because it was at the surface not long ago in geological terms. Deep basins with no ventilation go stale. This one gets refreshed, and everything living down there depends on that. So the sea nobody visits is doing 3 jobs that touch everything: moving heat, burying carbon, and delivering oxygen to the deep. And now the part that closes the circle. Every one of those jobs requires surface water to become dense enough to sink. Dense means cold and salty. And the entire length of coast we've followed, from the strait at the top to the cape at the bottom, is a conveyor for the one substance that prevents water from becoming dense: fresh water, arriving in enormous quantities in solid form, on a current that never stops. So here it is one more time. Almost none of the ice in the Greenland Sea was made in the Greenland Sea. Take that as a fact about navigation, and it explains why the coast is shut, why the harbors don't exist, why 14 men on a coal house went 1,000 miles they never chose, why a supply ship sits stuck in front of a town in October. Take it as a fact about the ocean's plumbing, and it says something else entirely. Every floe crossing Fram Strait is a shipment of fresh water pulled out of Siberian rivers and Arctic melt and Pacific inflow, held in storage for years, and then delivered south to the exact latitudes where the ocean needs to be salty enough to sink. The hostility and the climate function are the same delivery, seen from 2 positions. I want to be careful about where that lands, because there's a version of this that overclaims badly, and it gets repeated constantly. The honest state of the evidence is this: we know the lever exists. Freshening at the surface suppresses convection, and we watched it happen when the Great Salinity Anomaly moved through the subpolar Atlantic and shut down deep mixing in the Labrador Sea for years. We know Greenland sea convection is shallower than it was in the 1970s. We know the ice sheet is losing mass and that Arctic ice export continues. And we also know that across 2 decades of continuous measurement, the overflow through the Denmark Strait has kept running at essentially the same rate, which tells us the system has more slack in it than the simple story allows. Anyone who tells you they know where the threshold is, or when it will be crossed, or that it has already been crossed, is telling you something the instruments do not currently say. What the instruments say is that the lever is real, that a hand is on it, and that nobody has a reliable reading of the setting. That's an uncomfortable place to stop. And it happens to be where the evidence actually is. If the cold end of the map is your kind of territory, subscribing keeps you supplied with it. And the like button is sitting right there if this water earned it from you. But the thing I actually want from you is in the comments. And it comes from the strangest thing this coast has ever done. In 1884, a hunter on the southwest coast of Greenland found a document with a dead captain's signature on it, writing a piece of ice that had crossed the top of the world for 3 years to get there. Nobody sent it. Nobody steered it. It simply arrived because there's a current, and the current goes one way. So, tell me about something of yours that traveled without you. A message in a bottle. A bag that got lost at an airport and came back 6 months later stamped by a country you've never been to. A letter that took years. A photograph somebody found and returned. Something that got somewhere on its own and turned up in a place that made no sense until you understood the route it took. I'll be reading those, and I suspect a few of them will be better than anything I could have written. Somewhere north of here right now in the dark, a flow that formed off Siberia the year before last is passing 80 degrees north between Greenland and Svalbard. On its way to a coast with no harbors, carrying fresh water it will not release for another year and a half. Nobody is watching it go. It goes anyway.